Ok, well, eu falo pouquinho português, mas I'm gonna speak English because my Portuguese is not that good. But I'll be happy to answer questions after the panel is over. My name is Gonzalo Frasca. I make video games. I work at a company called DragonBox. I'm from Uruguay, and I'm gonna be discussing some of the things we've been doing on this last 5 years at DragonBox, basically creating games for kids to learn mathematics. And learn mathematics in an engaging and hopefully fun way, but also importantly, in an effective way. So let's begin. I'm gonna show you a short video of one of the games we created. It's one of our more popular games. It's a game that usually people play at home, but also can be used at schools. Not just at schools, but also high schools. So here you see it. It's called DragonBox Algebra. And we can see a kid doing algebraic equations. It's a tablet game, okay? The interesting thing about this is that the boy who's doing this is 4 years old. And this is a game that actually can teach how to solve algebraic equations that usually you learn in high school when you're 13 or 14 years old. It doesn't teach you algebraic thinking. It teaches you the algorithm on how to solve the equations, which is hard enough and which is something that much older students struggle with. You may think this is just a gimmick, something that, well, okay, it's cool, but it's not really useful. But I think it's important because it shows not just kids, especially adults, that things in math that we think that are complicated can actually be learned in a fast and fun way if they're presented in an engaging and interesting way for children. This is how it works. This is a card game. I mean, it's online. You can play it on tablets or on PCs. But it starts with some animals and some monsters. And as it progresses, it becomes more and more abstract. And this is an equation that a 6-year-old can solve. I was in Uruguay, where I'm from, in a conference with teachers and students. And I asked who could solve this. And only the kids and the math teachers raised their hand. So this is to give you an example of, again, the power of video games. I'm not here to say that video games are the magical solution for schools. I'm not saying that. But I'm saying that they can be useful, and more importantly, they can inspire us to think in a different way, in a playful way that connects better with children and challenges them step by step. So I'm going to be telling you about a project that we're doing with school kids, first grade, 6-year-old kids. Right now we have a pilot program in Norway and in France with 650 students that are learning mathematics, the full curriculum, with a new system that we collaborated, game designers, teachers, pedagogues, illustrators, musicians, storytellers, to create a math solution for learning math that actually is both, we're hoping, it's both engaging and effective. Because it's first grade math, the most important challenge is to make sure that children have a strong number sense. If you're not a math teacher, you may not know what number sense is. Number sense is the ability to deeply understand numbers. It's something that if you don't develop at a young age, it's one of the most accurate predictors of math failure later in school. To give you a simple example, children with a weak number sense, they see numbers just as a number line, just as a series, as a succession. They sing the numbers, 1, 2, 3, 4, 5, and they count like that, but they cannot understand how numbers are connected. A child with a strong number sense understands that numbers are a series, but also understand that 4 is 2 plus 2, and it's also 1 plus 1 plus 1 plus 1, and it's also 3 plus 1, and it's also 1 plus 3, and it's smaller than 6 and bigger than 2. They see, I would say that children with a weak number sense see numbers in a linear way. Children with a strong number sense see them as a network. So we know, and we have known this for a long time, that in order to learn math, math is better learned with manipulatives, with physical objects that we can play with. And one of the most classic ones are the Kuisner rods, which I'm showing here. So one of the first things that we did was to see if we could push this tool that was invented in 1920 further into the 21st century, if we could expand it in a useful way. And what we did, we created a digital version that is not supposed to replace rods, but it's supposed to complement them. In order to do this, we worked with a French pedagogue called Rémi Briciot, who's actually also teaching 2 classes right now with this method and trying to see how we can integrate the digital and the physical world. So I'm going to show you, this is a game that actually we use on first grade. And these are basically Kuisner rods, but that they can eat each other. There we have 1 eating 1 becomes a 2. And I just sliced a 6 into 2 3s, that's a 5. I mean, all these manipulations that you can do physically with the rods, but you can easily make additions with the physical rods, but it's hard to make subtractions because you cannot break them. Here, you can do it without a problem. So this is a tool. One of the problems that we discuss with teachers in Norway and in France is that we know that manipulatives help young children, but manipulatives are expensive. They're hard to, the logistics are hard. You lose the pieces, they break, kids swallow them, so that can be a problem too. So we decided to see if we could create a toolbox of different tools, different manipulatives to teach each one of the concepts that young children need to know for mathematics. So the first step was, again, creating these numbers, this representation of numbers called the nums, which, again, serve many purposes. They can be combined, they can be sliced, you can sort them, order them, and you can also compare them. Okay? This is just a small step over the traditional method, but we went further. So we're working with 18 teachers in Norway and 2 teachers in France. And the first thing, when we started working together, teachers really wanted flexibility. They said, some subjects, I've been teaching them for 10 years. I know how to teach them. So I don't want to use your method for that. So we had to figure out together a way that was modular and allowed the method to be used in certain areas, but not all of them. As game designers, it's also very challenging, the same challenges that teachers have when you can only iterate once a year, right? I mean, like, you teach something, and if it doesn't work, you have to try again in the next year and a different technique. Well, the same thing with making games. We tried to test a lot so we could go faster. We didn't have to wait a whole year to come up with better solutions. So, why do children love video games so much? And more importantly, how come that kids can learn video games so fast? Video games can be learned very fast because they have something called a tutorial. And this is how it works. At first, if a kid gets a new game that he never played with it, he'll start pushing buttons and see what happens. It's the experimentation phase. Okay? Once he discovers what's going on, then he gets a level of practice. Okay? And at the end of the level, there's a major challenge, which is called the boss battle. And that's like a test. It's like the assessment. If the kid can figure out that problem, then he moves to the next level. So we took that same structure, and we worked together with a lot of people, tried to see if we could make that structure work in real classrooms with the time constraints and all the real constraints of real classrooms. So, this is one of the manipulatives that we have, and this is how the class will begin. The teacher for 20 minutes will just hand in this manipulative on a tablet to children without giving any instructions. The children never seen these signs on the middle. They have never seen it. They don't know how they call it or what they're good for. So, kids experiment for 20 minutes, and they start. I just put a version with numbers. So, if you put, I'm going to put a 3 there, and the sign changes. I put a 5 there, and the sign changes the other way. So kids start experimenting. After 20 minutes, they stop experimenting, and they discuss with the teacher. They go to the textbook, and they find this image that the teacher is going to use to put a name on what they just discovered. So first, children will try to explain with their own words what these signs are about, but then the teacher will say, okay, let's go to this page, and this is called the equal sign, this is called, I will ask questions to the children, right? When would this sign be appearing? Is 4 bigger than 3? But is 4 bigger than 2 plus 1? All those questions. Up at this point, the kids have experienced these concepts. They know that they just learned the names about it, but they haven't really learned them. They haven't really incorporated them. So later on the class, they can do this in the class, or they can do this on homework. On the tablet, they play mini games. The mini games are for practice. And basically, so it's the next step. Basically, it's a game that you play over and over and over. This is the first version. We're gonna keep improving it, but you just draw the sign, and the crocodile or jacare will eat not the bigger in size, but the bigger in quantity. Okay? And you have that bar at the side that keeps going up. And you do this dozens and dozens of times until not only you experience the concepts, but you also learn how to use them correctly. Of course, if you make a mistake, you get corrected. That's the equal sign. And so once you have reached, you get a star, so you really, really have practiced this a lot. The interesting thing about this is that the feedback is immediate. If we did this on paper, the feedback would take 1 day or even 1 week. And if I have 20 exercises and I make a mistake on the first one, it's likely I'll make a mistake on the other 19. The good thing about video games is that I get corrected immediately, and I can correct myself. So the practice is not only digital, we also have printouts, photocopies, so kids can transfer to paper. And finally, they get assessed on another textbook. And this is the important thing. I mean, the assessment pretty much looks like a regular textbook. The important thing is that kids are not assessed, all of them at the same time. They only get assessed once their formative assessment tells that they're ready. And this is crucial. So it means that I could be tested today for this chapter, but some other kid who's faster would have been tested last week, and some other kid who was like sick or is a bit slower will be tested next week. We only test children when we feel they're ready. What is the point of testing children when they're not ready? They become frustrated. If I tested you about, I don't know, Uruguayan geography, you probably will fail, and you feel bad. Well, that's what happens pretty much every day in a lot of schools. So, and again, this is an experiment. It sounds easy here on my presentation, but then on the day-to-day, on the school, it doesn't work as smoothly, okay? And that's part of the experiment we're doing all together. Again, a lot of designers and teachers. We want to find a way that is realistic, and we have failed and improved, and some part of this are not yet figured out and may not work. So that's part of what's exciting, but the good thing is that both the teachers and also the students are involved. The parents accepted this also, and they know, well, that if something fails, we'll work really hard to try to fix it and make sure that all the kids can learn. One of the interesting things is that when we first started the pilot, of the 650 kids, 3 of them solved half of the year in the first week. They were really fast, and we were not prepared to them for that. And we usually pay attention to those who are slower, but what about those who are faster? They also become bored, they can also become a problem in the classroom, and well, so we're also trying to figure out more challenging games and tasks for them. I'm not gonna explain to you, of course you know, I mean, how complicated this can be, especially also adding technology. This is not a digital solution. It has a tablet, it has technology, but it also has a lot of textbooks. And one of the most important things that we figured out on the first day, it doesn't require Wi-Fi. And all the teachers were like, great. But everybody else is using Wi-Fi. The thing is that Wi-Fi doesn't work well in schools. We all know that, okay? So we will include Wi-Fi eventually, but we tried to make a solution that works without that. That was the second thing that teachers said. Wi-Fi doesn't work, well, let's try to figure out a way that doesn't require it. So this example shows how this loop works, and every single subject on the curriculum works this way. I'm gonna show you first 2 of the important decisions that we take. First is that just like in Singapore math, we start with very concrete objects, and as the year progresses and as the lesson progresses, we become more and more abstract. You can see that the nums start as rods, and then they become the characters on the screen, and then they become a more abstract version, and then they become the number. And the other thing is that we don't just work with the screen, okay? Technology companies want to tell you that everything can be solved with screens. No. First, it cannot. Second, we don't want kids to be in front of a screen all day in a school and then go back home and be all day in front of a screen. So we balance, just like a diet, we only use the screen when it's needed. We also have physical books and physical manipulatives and toys. But more importantly, it's like some kids might learn something and be fluent on the tablet, but then it's not obvious they can transfer that knowledge to the physical world, to the reality, or to the books and writing. So that's also why we use different media. I'm gonna show you, this is the theory textbook. This is how we introduce numbers. That's number 2. So we compare it with 1, which is the violet one. And this is the house where he lives. And that's another thing that first, we're very visual because young kids cannot learn. So we try to, these are word problems without words, like cartoon problems. The 4 bunnies only have 2 carrots. So we model that with the rods and ask how many carrots will we need so every bunny can have a carrot. These are the complements to 10. So 9 gets on the top of 1, 1 gets on the top of 9, 8 and 2, 7 and 3, and vice versa. Some geometry, because this is a program, the curriculum that they use in Norway. Of course, curriculums, they're not that different all over the world. One of the things also that teachers usually say, oh, okay, but if it doesn't fit my curriculum, we also worked so it could be modular and we could adapt to different things. As a design challenge, it's very, very different from making traditional video games. I mean, traditional video games, you work very fast and you don't have to please, you only have to please the player. Here you have to take into account the needs of the player, of the teacher, of the administrators. So it's a very, very complex game to make. Another important aspect is that we have storytelling. We have stories, literature. This is a story about number 2. Number 2 is very helpful and he helps his friends. And this is something that also we had problems when we were creating this because teachers would say, I only have very little time to teach math and you want me to waste some of that time in literature? No, that's another discipline. But children, they are used to very complex characters and very complex fictional worlds outside of school. And if we want them to care about mathematics, there's no learning, there no emotions. So we work hard to make lovable characters that are not only lovable, but also have mathematical qualities that are coherent. These are not just characters. They're also representations of numbers, and every time you combine them, you're actually performing real math, just that you're just using a different form of representation. So I'll just show you one of the books. Oh, everybody's looking for 2, and 2 is hiding. He hides many places because he thinks his friends want to ask him for a favor, and he's tired. But actually, well, many things happen. But the most important aspect of DragonBox Cool is that we use manipulatives. And we created manipulatives that cannot exist in real life with physical objects. These are counting boxes that can count anything. If we want to make sure kids understand that numbers are everywhere, we should be able to use multiple forms of representations. So we just use regular numbers, but we can also use like a hand. And you can even count one box inside another box. And we use these 2 counting boxes. One of them is on base 5. The other one is subitized to 3. Well, that's a bit technical, but the idea is that kids should be able to see that counting could work in different ways and with different strategies. One of the essential things for young children to understand is that numbers are composed by other numbers. So one of the teachers suggested that we should be able to show that. And we try to say, okay, how can we do that? That's number 4, okay? Of course, you can slice it into 4 units. That's a €2 coin. And that's a €5 bill. But let's see inside number 4. So we created an X-ray machine. That's a manipulative, that's digital. It cannot exist in real life, but it allows you to look inside every number and see its composition. So you can count money. I can add, and you can compare, like I have €5 on one side, €2 on the other one. How many euros do I need in order to, and you engage children asking them questions, and you first announce it, then you test it, and then you make a conclusion out of that. This is not a game, it's more like a toy, again. And we're testing this on the smart boards. We project this on the blackboard. Of course, I'm sure you're all thinking this is going to be very expensive. And yes, it's expensive to create and expensive to incorporate, but it's an experiment. We're testing, we're trying to first see if it works better than other methods, and then we'll try to make it accessible for everybody. This is another machine that counts money, and it gives you change. We haven't created one that gives you social change. We hopefully will be able to create one of those. I don't know if the joke was translated, but well, you're supposed to laugh, but that's okay. This is another manipulative that counts up to 100. So it counts large numbers. And again, children play with this for a long time. They just like to pull the levers and try to discover by themselves. Here it's useful to see number placement. You got a 10 on the left and 5, and that's 15. So for learning larger numbers, you can use this machine and some other machines. So you have 2 10s, and now it's 27, 28, 29, 30, 33. Of course, you don't use all these things at the same time, right? I'm just showing you the available tools, and some teachers invent new ways of using them. Some teachers invent new strategies. Even some kids find some cool stuff, and we allow them to play this with the manipulatives in groups, because they will discover stuff and tell each other, and you can see kids getting up from one table to the another one and telling their friends, check this out, it's cool, and trying to figure out how these things work. So these are the physical rods, the traditional ones, but with the new characters that we use to complement the digital experience. And as I told you, we have mini games for practice. I'm going to show you the whole year, very fast, of practicing for addition. And what we do is, like, as I told you at the beginning, we use many different forms of representation. So we begin with the nums. So 1 equals 1, without even any signs. Okay? So a couple of weeks later, we'll move on to another one. So 3 equals. It's important that children become fluent in many, many ways to understand that numbers, they're not just what we call numbers, but that they're everywhere. That even if they're not called that way, you can count, you can see them in different representations. We use dice and dominoes, physical games, also for this. So 3 fingers equals 3. Then we move on to money. One of the problems that we didn't see coming is that in Norway, because everybody uses credit cards, children are not as fluent in money as they used to. So of course, in different countries, that will be different. But we were not expecting that. And these are some of the drawings that children have been doing about the nums. So, to sum up, this is a pilot that has been happening for 5 months now. We have changed everything many times. And I think what is important to get people who make games and teachers working together is that first, we all care about children a lot, but also we all face the same challenges. Because when you make a regular game, a traditional game like Candy Crush, there's no manual, there's no instructions. You have to learn as you progress. And that means that you start with a challenge that is not too hard and is not too easy. A challenge that is adapted to each player. And of course, traditional school tries to work that way, but it's very hard. So by combining the techniques that we have developed in these 2 different worlds, we can try to make it better for children. It is essential, I think, to understand that we don't do this to entertain children. It's not, I mean, a lot of textbooks just put children-friendly characters so it looks fun for kids. Instead of doing that, again, we really want to give them an experience that is complex. But again, we don't do that. Teachers are not clowns. We're not there to entertain them. But it's essential to understand that the opposite of boredom, the opposite of being bored, is not having fun. The opposite of being bored is being challenged. Humans evolved to take on challenges. Play is the way children learn the most challenging things. How to communicate, how to get along with other people, how to control their body. We're facing challenges in this century that we don't know how the future is gonna be. And everybody said that before. Everybody said that the world was changing too fast. Even the Greeks say that. But in the last 20 years, the world is really changing in a way that it hasn't changed before. For most of human history, you were either a farmer or a housewife. In the 20th century, you added being a worker, factory worker, or a bureaucrat in an office. But now, we don't know what's happening in the next few years. So how do you prepare children for a future that we don't know how it's gonna be? Well, that problem that seems so hard, it actually has already been solved. Evolution solved it. Humans control the world because we evolved to get used to very challenging climates, to very challenging geography, to very challenging threats. And how we did that? We evolved to connect two parts of our brain, pleasure with curiosity. And that's what play is about. We get a kick, we get happy, we get engaged out of curiosity. And that's how we learn. So if we can get that back into school altogether, I think we have a good chance to make kids learn and enjoy math. Thank you very much. Thank you.